question. Who thought these were easy? Okay, that's good. Who thought these were hard? That's also good. Because they're not easy questions. We actually we could spend a few lectures on each of them if you really want to dive into that. Today's lecture is a little bit like this. The previous lectures were a little bit about this. Tomorrow you'll get a lecture on profile and structure that is a little bit about this. And we're not even covering this one in this course. We will in a later course. Okay, so let's go through each of them. Why error per query and not a rock plot? Sorry, coverage versus error per query and not a rock plot. Who wants to? So what is the difference? Let's start there. What's the difference between the rock plot and the error per query? What's the same? That's easier.
The numerator.
I'm sorry?
The numerator is the coverage.
Yeah, well, one of the axes is the same, right? The coverage, they both actually have coverage on the vertical axis. Yeah? Sorry, I need to check if I have a slide for this. No. Let's just draw it, right? Coverage, that's true positive rate, right? So that's the same for both plots. But false positive rate, it's over there. It's the fraction of errors, false positives, as a fraction of what? This is what? True negatives plus false positives.
No negatives.
All negatives. How many negatives do we have in our database? Do we have more or less, more or fewer negatives than positives in our database? More, right? Yeah. Because if you have a particular query sequence, the number of homologs is limited. Could be still a lot. Could be maybe 10,000. But the number of typically 10 or 100 maybe, or even less. But the number of negatives, that's all the others, right? It's the needle in the haystack. The positive is the needle. The haystack is if you have a needle stack with some hay in it, it's the other way around. Yeah, but if you have a haystack, there's lots of hay. You don't really care about how much hay there is. You just want to find the needles. Yeah? So you don't really care about these negatives. If you don't use the false positive rate, but the error per query, the numerator is the same, false positives, but your denominator. Do we do it the right way around? Yes. So I get this. It avoids the negatives, because you're only counting. What is this? True positives plus false positives.
Everything you predicted is positive.
Because you're all your predictions, right? Because these are predicted, they're correct, and these are also predicted, and they're incorrect. They call it error per query. I have no idea why they call it error per query. Because there's only one query. It's error per hit or something like that. Yeah? If you have 10 hits under your p-value threshold or whatever particular scoring scheme your method uses, you predict 10, and it's 3 out of 10 are correct, or then there's 7 wrong. Yeah? So then your error per query is 0.7. No, well, error per, I would call it error per hit, or something like that. Anyway, they call it error per query. That's why I have this slide on it, which summarizes these things, because not all of them make sense, to me at least. Okay, so instead of false positive rate, we do error per query. Nope. There. Okay. Anything else about this question? Questions about this answer? Or answers about the question? No? Okay. So I think in this set of questions, this was relatively easy. So we'll go to question 2. How do these methods compare? And can you categorize them? Any ideas? I didn't get any questions about this question. I did get questions about some of the others. So who has an answer for this? Yeah?
It's found that in general, there were they compared methods in 3 different groups, which were profile, sequence, and sequence.
Yeah, so just repeating so everybody hears, and it's also on the recording. So there's sequence methods, sequence profile methods, and profile methods. So can you guys give me an example of a sequence method? Blast, right? And sequence profile? Blast. Yes? Okay. And then profile we haven't covered yet. There will be more on this in algorithms and sequence analysis next period. Okay. Yeah. Anything else?
Yeah. They found that in general, they used PRC, which is the profile method, and they found that in general that one was the best, and most of the profile methods, I think maybe all of them, beat out the others in terms of their ability to find homologs, but
Yeah.
they were most expensive computation.
Yeah. So PRC was. So if you, I have a pen. Something messy with blue box shouldn't be there from the start. Sorry. Drats. Yes, that's better. Sequence methods, there's only one that they included. Yeah, that's BLAST. And it, particularly in this plot, this is one where they no, I'm not going into details. There's different plots, and this is one of them. But the differences between the methods are bigger in this comparison, but I don't want to explain to you guys why now. So this is sequence, just quite poorly. This is sequence profile, Hammer, SciBlast, SAM, and H8 search. Right? And then profile, and it's quite convincing, right? So if you're looking for remote homologs in particular, never go for a sequence or even sequence profile. It's just not good enough. It is a bit funny, isn't it? Because you are looking for homologs of this one sequence. And they're easier to recognize if you're not searching with this one sequence, but you're searching with a profile that doesn't look like the sequence you started out with. Well, a little bit, obviously, because it should be the profile of the family this sequence belongs to. But searching for a good hit for your input sequence works better if you don't search with the sequence, with something that is broader than just the starting sequence. Why is that?
It's less strict, so it allows for some.
It's less strict. How can it be? How can you be better at searching if you're less strict? Sorry?
It doesn't converge easily, can go farther.
I think that's in the right direction. So it doesn't converge that easily, and so you can go further.
And
Anything?
search in a bigger
Yeah.
space.
So because you're searching far away, right? So if you're searching only with your input sequence, then it's hard to recognize things that have similar patterns, but are they could be different on all the details. Okay, so if you're just using your input sequence, so if you're looking, so maybe you've had this situation that you're going to pick up somebody from the airport that you haven't met before, and you only have this one grainy picture that you found online of this person, and you have to recognize it, right? That is a hard problem, even for our brains. They're supposedly good at pattern recognition. It's quite a hard problem. If it's somebody you know, your mental image is both more precise and more forgiving for recognizing this person, because you've seen this person in many, many different situations, different lights, different directions, different angles, different hairdo, different glasses, different clothes, and so on. And then immediately when you see somebody on the airport, you can recognize them. Because if you only have this one photo, it's very hard to recognize. Yeah? Okay. So we're not going to go into profile relations in this course, but this gives you an idea. This is remote homologs. If you're zooming into this area, this is where the closer homologs are. Why can I say that? Why are the closer homologs here? Okay, so this is where you've made and there should be easier to recognize, right? Closer homologs, so you make fewer errors. But there's a more direct reason for why I can say this. Remember how I explained it for the rock plot, but it goes the same for this plot. Yeah? How this plot is created. Yes, exactly. So if you to create this, and it's for glasses e-value, but for other methods they might use a slightly different metric for their scoring. So it doesn't really matter. You have a threshold for what you consider positive predictions from your method, and if you make it more strict, you're predicting less. You're making fewer errors. You're also getting less coverage, but you're typically predicting the easy cases first. If you make your threshold stricter, you're only predicting the easy cases. That's why you're making fewer errors. But there's also obviously the closer homologs, because those are easier to track. Yeah? Okay. And you might see that if you're really going into the close homologs, for example, HH search here is performing less than complex and PRC, but if you trace it back to here, there's a spot here where it's actually, for the closer homolog, it's actually slightly better. Yeah? So if you're looking for close homologs, you might not always want to go for profile search. That's better for remote. Blast always ends up at the bottom. Don't use blast. Why do people use blast? Because everybody's been using blast for ages. It's easy to what's the word for that? It's easy to do, what do we call it? When you need a reason to do something. You write down the reason. This is called justification. Yes, it's easy to justify. Everybody's been using blast for decades, so if you use it, it can't be that long. Well, not for close homologs. Okay. Yes, that's enough for question 2, I think. Let's go back to the questions. Where were my questions? Oh, there. Here are questions. 3. Clear about question 2? Yes? Okay. Also, the point of these questions aren't really that there is a good or wrong answers, right or wrong answers. It's really to think about it, right? Because there's different things you can say. Okay. So, question 3. Which database did they use? CATH. Yeah? What is CATH? It's a bit like SCOP. SCOP is structural classification of proteins. Yeah? The CATH is also structure. So, that's SCOP, right? Structural classification of proteins. CATH is also an acronym. class architecture. Homology, yes. And what's the T? Topology. Topology, right. Okay. So it's also structural classification, but it's organized slightly differently. It should in the end be the same. Path is actually based on a computational method. And that means they've been able to keep up with the growth of the protein data bank, and that means that there's more proteins included in CAF than there are in SCOP. SCOP was originally the work of one man, Alexei Merzin. Ask Jaap about him. He has some very nice anecdotes about this guy. He just looked at a protein and said, oh, this belongs in this family. And then looks at the next structure, oh, this family. He kept doing that. Like when there were like 5,000, 6,000, 7,000 proteins in the protein data bank, he would recognize all of them and put them in the right family. There's a method built on that database trying to recreate what Alexei Merzin was doing manually. So there's scope 2, but it's still work in progress for the last 15 years or so. For some reason, it's still difficult. But anyway, they're sort of both doing the same thing. What's the point here? Yes, okay. So they used, why did they use CAF? Anybody know? Did you, maybe you looked at the references at the end? There were a couple of papers referenced for CAF. Did you notice the pattern? You didn't? The papers by CAF were all written by, at least included in the author list, Christine Orengo, who is the senior author of this paper. Right? So it's her database. She started CAF somewhere in the 90s. And well, then if she does a benchmark paper on homology detection, obviously she uses her own database. Is that biased? Maybe. Is it smart or wise? Well, what do you think? Would you use your own database that you know very well because you worked on it for 30 years? Or would you use somebody else's database that you might also have worked with?
I prefer to define it.
You could use both, right? Could you use something else? Are these the only two options that you can choose from? Anything else that you could use? Yeah, you could use gene ontology, Go. Yeah. And then you use function to identify homologs, or as a way to distinguish putative homologs from unlikely homologs. You could use PFAM, right? Do they? I don't remember. Do they discuss PFAM in the paper? They do, I think. Yeah. Okay. There's lots of small but important tricks they do to get their benchmark data good for the benchmarking. If you're really interested in that, you might want to reread the paper and see if you can pick them up. Don't try to implement all that in your project, because you will run out of time. I mean, just mentioning it because it's really interesting, but there's a limited amount of things you can do, as I'm sure by the start of the third week you're starting to realize. You can't do everything in the given amount of time that you have. Okay, that was question 3. Anything else about question 3? So there will be a lecture tomorrow on profiles and structure. Bas is going to do that. So then we'll come back to this. Yeah. Question 4. Transmembrane proteins. So what's about those? Who wants to give a start? What's special about transmembrane proteins? They're in the membrane. So transmembrane proteins have both hydrophilic and hydrophobic regions. Let's first the other proteins, if they're not transmembrane. Cytosolic. Well, there's a class in between. There's membrane-associated proteins, but yeah, let's keep it simple. We have cytosolic proteins. They are soluble. They are happy floating in water. Yeah, make it simple. And transmembrane proteins, they're stuck in the membrane. Membrane has a hydrophobic part in the middle, and so for a protein to be happy in the membrane, it has to have a hydrophobic part in the outside. It's also will have hydrophilic parts because not all of the protein is in the membrane. It sticks through the membrane. Yeah, it will look a little bit like. This is the membrane. Then your protein will look a little bit like this. Yeah, this is not a real protein. And this is the transmembrane part, but this is still water. Yeah? Water. Yeah, and this is also water. Okay, so that's what's special about proteins, transmembrane proteins in a structural sense. What does that tell us about? What does it have to do with homology detection? Because otherwise, it's just a protein sequence, right? So nothing special yet.
So how to predict the structure of these?
It's hard to predict the structure of these. I'm not sure. Actually, it's relatively easy. Sorry? They have repetitive sequences. Yes.
Inside the membrane, they need to be, the amino acids need to be hydrophobic. So
Yes.
there are only a certain amount of hydrophobic amino acids. So there's only a certain amount of ways you can make them up.
So these have to be hydrophobic. Yes. But you're saying there's only so many hydrophobic residues, amino acids. Yeah. But there's also only so many hydrophilic residues. So that seems, but the thing is that it's very close. The point is that there's only a few structural topologies that will make a stable structure in the membrane. And basically the two, we'll get back to that later, but the two main classes are beta barrels, beta sheets all stacked around like a barrel, or a bundle of helices. And this, I don't think there's anything else. If you look at soluble proteins, the ones that are happily floating through the cytosol, they can have all sorts of weird combinations of alpha, beta, or different arrangements of alpha helices and so on. But there's only really two basic topologies of transmembrane proteins. So what happens then if you put transmembrane proteins in a structural classification? There's only two architectures, right? There's beta barrels and there's helix bundles. And then within those, there's only a limited amount of different variations you can have. So the odds, to draw in the evolutionary perspective, the odds of having convergent evolution in transmembrane proteins are very high. Because to be in the membrane, you have to get one of these two structures. I think we have to hurry on. Okay, that's one part. What was the other part? It's actually, so I'll just give it to you. In the interest of time. They're very hard to crystallize. If you can't crystallize a protein, you can't measure its structure. So that means we have very, very, very few transmembrane proteins in the protein database. I think it's about something like 1.5% or so. Whereas if you look in an average genome, 30–35% of the genes are transmembrane proteins. So we have 10 or 20-fold relatively fewer structures for these proteins. And so we have a lot less data to benchmark on. Okay. If there are no very urgent questions, then let's get to the practicals and